Okay, so we've got some data here. And the first thing you do whenever you get data like this is really to test for skewness and to test for outliers, because if there are skewness and outliers, then this can affect the kind of test that you'll do. There's no point in running a t-test, finding you've got a significant result, and then doing a test for skewness, subsequently finding you can't use a t-test because the data is too skewed, and then having to do a different test. It can be a very disheartening experience, particularly when you do the second test, you get a non-significant result when previously you got a significant one. So let's look at this. So the first thing is we probably want to do a test for skewness. There's a separate screencast on that elsewhere on the website. You can look at that. So let's here test for box plots. Before we do that, let's look at the data. The data, we've got participants to do a task, and we've given them 40 milligrams of caffeine or a placebo down here, and we want to know how long it takes them to do the task. This is therefore between subject design, and you can tell that because we've used here coding variables. So participant 1, remember, if you think of the rows as being participants and the columns as being variables or measures taken of that participant, then participant 1 took 44.5 seconds to perform the task, and the other measurement with them, which is pertinent, is that they were in the group that was administered caffeine. If you don't know what this means, then there's a screencast elsewhere which explains how to set data up in SPSS, which explains that when you do a between subject design, you need to use a coding variable like this. So if we look in here, we can see that 0 is placebo and 1 is caffeine. We've just simply used a number to stand for the variables here, because the levels of the variable, because SPSS can't actually do anything with words, so we need to give it numbers in here. The numbers don't matter. Here we've used 0 and 1. You could use 1 and 2, 2 and 3, whatever you want, and it doesn't matter which way around you put them. It doesn't matter, for example, in this case, that placebo is 0 and caffeine is 1. It could equally be the other way around. So let's go back here to the data. So we go from variable view back to data view. The first thing we might want to do is just to do a box plot. So let's have a look at that. We go to graphs, legacy documents, and then we find box plots here. We want simple box plots, and we want summaries for groups of cases. Okay, so we've defined that. I've already put these in. Our variable is time. That's our dependent variable. Again, SPSS isn't the most transparent in the way that it names things. So the variable is the dependent variable, and group, which is a condition, is the category axis. So if we click on OK here, we can see the box plot. Now, I'm not going to go into too much detail about what box plots are, but essentially that they're ways of determining dispersion around not the mean, but the median. Okay, so it's a kind of a non-parametric way of representing the spread of your data or the dispersion of your data. The thick black line here and here is the median. This is the upper quartile, this is the lower quartile, and the whiskers are 1.5 times the interquartile range. I don't expect you to remember this is all written down again on the website, but the interquartile range is the gap between the third and the second, and then the top of the first quartile and the top of the third quartile. So this box here is the interquartile range, and the whiskers are 1.5 times that. So this distance from the top of this cap here to the box is 1.5 times the height of this box, and the same here and the same here. Now we can use box plots to kind of give some idea of skewness, and we can see here that the boxes are pretty regular, that they're pretty evenly distributed, that the median's kind of halfway approximately between the top and bottom of the whiskers, and the median is in the middle of the box. So the data don't look to be particularly skewed. We can obviously test that by using a test for skewness, which is available elsewhere in another screencast. But what it also does is highlight potential outliers. So we've got one here, which is represented as a circle. So anything outside 1.5 times the interquartile range, which is this cap here, is represented as a circle. And the number here, 32, is the particular participant that is. It's not the value of the data point, it is actually the participant number. So if you went back and looked at the SPSS spreadsheet, the data view, you would be able to find out what that value is. Over here though, we've got somebody who, participant 20, who has got a star next to him or her, and a star is what SPSS refers to as an extreme score. It's not just an outlier, it's an extreme outlier. And anything with a star means that it's 3 times the interquartile range, or more than 3 times, or less than 3 times. So, I mean, it's bigger than 3 times the interquartile range. It could be above the mean or median, or below the mean or median. Basically what that means is that this number here is more than 3 times the height of this box, and you can kind of see that it is. So we might be tempted to remove this particular outlier. In fact, we probably will. But there is a slight grey area because of the way SPSS uses box plots. There's a slightly more approved of way of determining whether something is an outlier, which is to convert the scores, each individual score, to a z-score. I don't want to talk too much about z-scores now, but a z-score is essentially a way of standardizing the value of each score in a distribution, each score in a data set. Essentially what it does is to convert the value of each score into a standard measure. Z-scores are also called standard scores, and it basically converts it to how far that particular value, any particular value, it says converts it to how high or low that particular value is away from the mean in units of the standard deviation. Okay. Again, there's more on this on the website. So it does some relatively straightforward mathematics on the actual scores down here. So that what it turns them into is a number which represents how far that is from the mean in terms of standard deviation. So if a z-score or a standard score has a value of 1, it means that that score is 1 standard deviation above the mean. If it's got a standard deviation, if it's got a z-score of 2, it means that that score is is 2 standard deviations above the mean. If it's got a score of, I don't know, minus 0.6, it means that that score is 0.6 standard deviations below the mean. Okay, so plus means above the mean, minus means below the mean. And essentially all it does is take each value, take the mean away from it, and then divide that result by the standard deviation. It can be useful for many things, but one thing it's particularly used for is to determine whether something is a significant outlier. So to convert to z-scores, we go into analyze, and we go to descriptive statistics, and we get descriptives. The one we're interested in here, oh, I forgot, very important point. Let's go back. I'm sorry to mention this. This is important. In terms of converting to z-scores, when we've got a between participants design such as this, okay, what we need to make sure is that we get the mean for the caffeine group and calculate how much each score deviates from the mean in terms of standard deviations, and a separate one for the placebo condition. So we need to find the mean of the caffeine group, the mean of the placebo group, and then find out how much each score in the caffeine group deviates from the mean of the caffeine group, and find out how much each score of the placebo group deviates from the mean of the placebo group. What we don't want to do is to just find an average of all of these numbers, in other words from both conditions, and then find the mean of each one away from the overall mean. That wouldn't work. We need to do it for separate conditions. So this adds a little extra level of complexity on it in terms of the kind of thing we need to do. If this was a perfectly within subject design, then we wouldn't need to do this next step, because each variable, each level of the variable would be represented by a separate column. Okay, so what we need to do is to split the SPSS table into half, and we need to make sure that it analyzes the caffeine group separately and the placebo group separately. So to do that, we go to data, and then we find this option here, split file. So third one from the bottom. Don't do split into files. Again, it's a little bit one of the wrinkles of SPSS, is it's almost like it's there to kind of trick you. Don't do that. Split file. So we go to split file. Let's move this into the middle. So we've got the 2 variables here, time and group, and what we want to do is to split the file by group. So it analyzes the caffeine group separately from the placebo group. So we click on the one we want, and we want to compare groups. Okay, so it's the second option, and we simply move that into there, and we want to compare the groups based on group, which is the condition. We click on OK. Nothing really happens. It doesn't actually do anything there, but if we go back, it will have split the file. So what we now need to do is to find whether any of these are outliers, and we do that as I mentioned, by converting each of these scores to a z-score, which is the difference. Each score is away from the mean of each of the two conditions, measured in the units of standard deviation. So we've got to analyse descriptive statistics and descriptives. This option here, we want to put time in there. We don't want to put group in because we're not analysing z-scores of the group. Remember, group is just 0 and 1, so that wouldn't come up with anything meaningful. So the variable we're interested in analysing is the dependent variable, which is time. And this option here, save standardised values as variables. Standardised values, or standard scores, or z-scores, all mean the same thing. Again, SPSS has a slightly different term for it. Click that, and then we click OK. If we go back to this, it's now created a z-score of time. So remember now, how many of these would we say were significant outliers? Well, there's a simple method to doing this, and if any of these scores is plus or minus 3.29, it's kind of quite a specific number, plus or minus 3.29 above or below the mean, so that's what a plus or minus means, then we would say that that data point is a significant outlier at the p is less than 0.001 level. There are different numbers that are used, but I think most people agree that 3.29 is a reasonable, is big enough to be an outlier. I think anything much smaller than that we can actually put into a t-test, put into an ANOVA, and these tests are robust enough to deal with that. So let's have a quick look at these numbers here. We can see that this is this data here, so 32.50 is, I mean, you can work this out if you find out what the mean is, but there's no point because it's telling you. This data point here is 1.56, if you like, standard deviations below the mean because of the minus. This one here, 45, is 0.9 standard deviations above the mean because there's no minus. And we can keep going down here. Now, if we go back to our original output and have a quick look at the box plots, participant 32 and participant 20 seems to be the problematic one. So 20 and 32. 20, let's look at 32. In fact, rather annoyingly, what's happened here, I've just paused the video for a second, is in the process of splitting the file, what SPSS has done is reordered the data. So it's no longer 32 and 20. I've just redone this, and now it's participant 12 who's the moderate outlier, and participant 40 who's the extreme outlier. The reason why it's come with two box plots rather than one is simply because we split the file so it does them separately. So let's go back to the data and look at these two potential outliers, 12 and 40. Well, here's 12, and we can see that that is 2 standard deviations below the mean, which is substantial, but not greater than minus 3.29. So we could probably accept that one. We don't need to do anything with that particular participant. We can keep them in. They are an outlier to some extent, but not a significant outlier at the p less than 0.001 level. We go to 40 here. We can notice that this score of 8.50 is minus 3.7 below the mean, standard deviation below the mean, which suggests that this is a significant outlier. There's no probably about it. It most definitely is. So this data point should probably be altered, and there's some information on how to do that on the website. Essentially, you take the score of the next lowest number and add 1 to it. That's a convention, but there's more information on that. So sorry about that. SPSS does have this habit of messing things up, as it just did there for me when it completely reordered the data and made the outliers different numbers. I hope that didn't impair your viewing too much. Thank you.